Okay, so welcome back. So let's continue with building towards threads. So data structures needed is not going to be in the form of a threads control block. You use a threads control block when you have a lot of memory. Here we are very tight on memory, so we already reserved 4 banks, right? 8 bytes each, so 32 bytes for the general purpose registers R0 through R7. We do need to save the additional registers, including your program counter, A, B, DPTR, PSW, on some stack. And then they get popped off, okay? If you have actually separate space, you don't have to use a stack, but then stack is kind of the natural place for that. And then the stack pointer itself has to be saved somewhere, and it itself can't be saved on the stack. Why? Because you wouldn't know where the top of the stack is, right? So the SP itself has to be separate. So we use a separate saved stack pointer array, saved SP array. Okay. Now, for each thread, that's kind of the memory you need. In addition, the threads manager would also need to keep track of a number of things. What are those? Well, for now, let's think of a bitmap, which is like a set, right, indicating which thread ID is active with a real thread running, which one is not. And you could keep number of threads, but is that really necessary if you have a bitmap? Probably not. So you could or skip that. And then the current thread ID, you have to know which one is active. Okay, so that you can do, or you could, again, use a separate bit mask for that. You get to decide. Okay, and there may be a few other temporary variables, maybe for the purpose of doing scheduling and other things. Okay, so what I do is I actually already implemented this, and I organized this as 3 source files. One is test co-op. That's for the testing of the cooperative threads. So it actually has the startup code, the main program, producer, consumer, and also the variables. There's cooperative.h and cooperative.c. The .h is the header file. So if you want to call from your application to the threads, you have to do #include cooperative.h to get the API and type declaration. Cooperative.c is the implementation, and it contains a bootstrapping code that's called by the startup code, and it includes implementation for thread creation, yield, and exit. Okay, and so what you need to do is you take my template, name them as these 3 files, and I'll give you a make file so you can compile with just make. Okay, and I'll go over the individual files. Cooperative.h, that's the include file. So it looks like this. So you don't have to actually change this. So what does it look like? It has #defined max threads 4. You should know that. We support maximum of 4 threads. Can't be more, there's just not room. And we do type def char thread ID. And so really all you need is 0, 1, 2, 3, and maybe -1. But then you can't get any type that's smaller than that. That's big enough, right? You can't do half a byte. That's not a real data type. And then type def void paren star function ptr close paren void close paren semicolon. Everybody understands how this works, right? Yes. Or haven't you seen this in C? You should have seen this in C. That is to declare the name function ptr as the name of a type. What type is it? It's a function pointer. So it takes a void type argument, which means no argument, and it returns a void type, which means doesn't return. So that's the type declaration for a function pointer. You just named function ptr. So you should know this. If not, read up on this. And so why would we need to declare a function type? Well, because you need to pass a function pointer as an argument to thread creation. You saw that in pthread create, right? And in a few callbacks, like signal also would take a function pointer as a callback. So anytime you have to pass a function pointer, you need a type for it, and this is how you declare it, okay? So basically, paren to protect star and then the name of the type, and then followed by the argument type list, okay? So type that void, so that this void is really the return type of this function pointer, and this void here is the parameter type or the type signature, okay? So once we have this type, we can then use it to declare thread create. Its argument is a function pointer and named FP. And then it returns a thread ID as its type, right? And then so that will create and start a thread that runs the function pointed by FP. That's how you read it. Now void thread yield, that takes no argument and returns nothing. Unlike Python yield, can take a value you kind of yield to whoever is calling you, and then it itself returns a value that's sent by whoever is calling you at the next time, right? Here, no, we just do the most straightforward. You can't yield any value back, and you can't receive any value, just so avoid both places. So what does thread yield do? So it allows a thread to voluntarily give up control. So then returns control to who? Well, to the thread manager. Well, what's a thread manager? Well, it's the program that gets started before main starts, and so that when you it's there to manage the threads. It's the code that allows you to create and destroy threads, right? And so this basically says let somebody else run. I'm voluntarily giving up control, and then of course the trust is that at some point later the thread manager allows it to run again, right? So then when it runs, it continues running that statement after the yield, okay? And then you have void thread exit void. For now, we're gonna skip implementing thread exit because to be compliant, you need some kind of join or detach, but you could actually do away without exit. In fact, you can even write code without thread exit. So for now, we just declare it as a placeholder, but we don't need to do much with it. I'm sorry? No, exit means the thread just is done. Doesn't want to continue anymore. So it gets recycled. Yield means it still wants to continue running. Yeah, I mean, this is same semantics as pthreads, pretty much. Okay, so test coop.c. So I give you the template that looks kind of like this. Okay, so one little change. It should be data instead of idata. I mean, it'll still work. So I'll just make the change right here because yeah, okay. So do # include 8051.h. So if you install SDCC properly, you should find this. And then cooperative.h, that's our .h file. Data at address var. So that is a way for you to declare your own global variables. Okay, and these are visible to all the threads. And in case you're curious what's different between idata and data, so in terms of code generation, there's a little bit difference in that data gives you the direct addressing in the range 0 to 127 or 7F hex. Now, idata is really for 8052. 8052 is an enhanced version of 8051 in that it can expand the memory by another 128 bytes, but they're indirectly addressable only, and they have the same address range as your SFR. So from 80 hex up to FF hex. But they are indirectly addressable. So you could actually put a stack there, or you could do all the table lookup with the indirect addressing. But anyway, you don't have to know about that. And in terms of code generation, if you do data, actually generates higher quality code compared to iData. I already fixed that in the template. So void a producer, void consumer, so no surprises there. You should know how to write the code by now, or look at some template and figure out, right? The only thing is for the cooperative version, somewhere you need to insert what? Thread yield, right? Otherwise, it's just going to hog the CPU for forever. And main does what? Well, spawning the threads, and then, or you could spawn one thread and then run the other thread, right? So, and then the rest is just we've seen before. That's a GS init startup, and then it has to do some bootstrapping. I think I went over this a little bit before, but okay. And then these are just to override the library functions for clearing RAM and all that. We don't use those. But this is to suppress linking code we don't want. And the startup will do an L jump to bootstrap. Okay, and then why a little underscore in front of bootstrap? Well, remember, all the identifiers in C, when you go to assembly, they get a little underscore in front, so that the you can tell whether this is code written in C or written in assembly. Okay, so if you want to call some C function, you always put an underscore in front. That's how the compiler generates the assembly. Okay, and then in assembly, your own identifiers don't have to look like that. And so on startup, it jumps to bootstrap. Okay, so, and then we'll talk about how bootstrap should look like. So the idea is very similar to the Python code, but you do need to remember to call thread yield, right? And then you pull the buffer. If it's full, then call yield. And buffer is available, then you make the next item and then mark the buffer full. The consumer, what the consumer needs to do is somehow consume it, right? Or indicate it's consumed or received. So what does it have to do? Well, it has to deal with two sides. One side is to grab to pull the buffer. Is there anything for me to grab? And if it's empty, then it yields. But there is some data already deposited by the producer. It reads from it and then clears the flag, right? But then what does it do with that data? How do you debug it? Well, we would then take that data from the buffer, write it to UART. And you should know UART by now, right? And here you could do the interrupt version, or you could do the polling version. So, I mean, just to make it easier, let's start out with the polling version. Okay, so even though it's not as efficient, it's okay. So then if it's polling UART and TX is busy, just call yield again. So consumer would need to yield in two different places. One is when it's polling the buffer, the other is polling the UART. Okay? So whereas the producer does a yield just for producing, because it doesn't have to depend on anybody else. But you could certainly do a version where it's polling the UART RX for any byte as its source, and then it would do a yield. Right now, I'm just doing it somewhat asymmetrically. UART only for output, not for input. Right? Okay, now, so main, you should know what it does. Main has its own thread created by the bootstrap function, and we'll look at bootstrap shortly. It does need two threads, so it has the option of creating two threads and run them, or it could create one thread and it itself runs at the other thread. Okay, either way is fine. But in either case, they don't return because we haven't really implemented the exit yet. But exit, yeah, we'll just do that another time. Okay, now cooperative.c looks kind of like this. So this is the implementation of your bare bones threads package. So it does the include #include8051.h, cooperative.h, and then declares a number of variables, as much as you need or as little as you need for the threads package itself. Now, two macros are defined only within cooperative.c. are named save state and restore state. You might call them save context and restore context, either way. But I just thought save state, restore state would be okay. And then it does need to declare extern void main void colon semicolon like this. Why? Because it's just declaring this to get the name main, and then the linker will resolve this. Because the bootstrap function actually is the one that calls or jumps to main, right? So in order to write this in C, well, C requires you to do an extern like this. You don't have to have the body of main in here. You just have to have the type signature, right, and then the identifier name. So bootstrap, void, and then this is where you have to fill in some code. On startup, what does it have to do? What does it have to set up enough so that you can kickstart main, and then main would run as thread 0. Okay, that's the trick. And once you get bootstrap, well, bootstrap actually has to call thread create to do much of the work. So thread create is a core function, and thread yield basically is doing the saving state, restoring state, with the scheduler in between, right? Picking the next one to switch to. Thread create is really to set up the context so that it's ready to be restored, okay, or returned to. But it's just setting up the context. And exit, we'll just do placeholder for now. Okay, so there was a question earlier about where the stacks would be located. So, well, here, I think you do have a number of choices, but the stacks are going to take up quite a bit of the space. So just, and also how many entries is enough, right? Because think about this. When you call a function or subroutine, it takes up 2 bytes right there. So it can't be that small. And which registers do you have to save? Accumulator, B, DPL, DPH, PSW, right? Or at least those. And so that's already 5 bytes. And then plus 2 bytes, 7 bytes. So if you allocate only 8 bytes for a stack, is that going to be enough? That's a little too tight, right? Because what happens if you take an interrupt? It gets pushed on the stack too, okay? And then that means if you allocate only 8 bytes, you're very likely to overflow your stack. So let's go up a little more. So how about 16? Okay, 16 seems a little more comfortable. And besides, you can actually afford to make it maybe 1 or maybe 2 levels of call. Takes up 2 or 4 bytes, maybe push 1 or 2 registers. So that's already putting you about 9 or 10 bytes. You still have 6 bytes to go on your stack. And the stack comes and pushes another 2 bytes. Okay, you're kind of tight, but then within reasonable threshold. Okay, so I think 16 bytes seems like good enough for a bare minimum threads. But if you use 16 bytes for one thread, 4 bytes, 64 bytes. That's half of your memory right there, right? So, well, if you want to do half of your memory, well, might as well do align it, right? So, might as well use the second half of the memory. So 40, 50, 60, 70, right? I mean, hex is 16. 16 bytes per hex, right? So 40 to 4H could be for thread 0, 50 to 5H for thread 1, 60 to 6F for thread 2, and 70 to 7F for thread 3. That seems reasonable, but that's already half of your memory. So that means you squeeze your memory down to quite a bit less now. So your register bank is already 0 to 7, 8 to F, 10 to 17, 18 to 1F. So that's already taking up 32 bytes and 64 for the 4 stacks. So you have 32 bytes left for your globals. And some of them need to be used by the threads manager. And in fact, threads manager has to also save the stack pointers, remember? Right? Stack pointers itself couldn't be saved on the stack because otherwise you wouldn't know where the stack is, right? So then you'd probably need to do 30, 31, 32, 33. Although there's one trick you could do, which is if you push the save stack pointer as the first thing, or at the bottom of the stack. So technically speaking, your stack would be 15 bytes instead of 16. That might be one way. So that way, you could save these 4 bytes. It's up to you what you want to do. But for now, I'm assuming save stack pointer is in a separate 4 byte arrays, right? Each SP is 1 byte. Okay, so so that means you do have just a few more bytes. Bitmap for the active threads might take 1 byte. Current thread ID may be another byte. Other temporaries, right? Maybe. So that's a rough layout. You could get to decide how you want to lay out your memory. Okay, and then there's a few more bytes left for the FIFO and then producer-consumer shared memory space. So let's look more at what you need to implement. So cooperative.c, that's the implementation for the cooperative threads package. So earlier I mentioned there's a macro called the save state, another macro called restore state. And we use macro for several reasons. One is it gives you complete control and you don't pay any overhead for calling a separate function, returning from it. Okay, but if you do this for real on a like Unix type system, or you are likely to use set jump and long jump for this purpose. But for now, we'll just do these 2 macros. So conceptually, not very difficult. Okay, so the macro is really just inline assembly code. What it does is it pushes ACC, pushes B, pushes DPTR, pushes PSW, right? And then now, when you push PSW, that's actually kind of nice because remember the register bank select bits are inside PSW. So as part of saving and restoring PSW, it already takes care of switching the register banks for you. That's good, right? That makes your threads more efficient. Now, you do have to save the stack pointer for the current thread into the save SPS location. So then later you can retrieve it and then use it. We do it as C macros. And then restore state is really the reverse of save state because you have to do it in reverse order. So in save state, last thing you store is the top of the stack, right? And you don't really know each time where the top of the stack is going to be. So that should be in some variable. Restore state, first thing is you restore the save stack pointer, point to the top of the stack. Then you can do the popping. Okay, so it's one is the exact opposite of the other, including the opposite order. And the bootstrap, we saw that on power up, there's an L jump to bootstrap, and that's the one that sets up the first thread to run main. Okay. So let's do some illustration of what this would look like. Once you have a good idea, then you probably would know what it takes to write the code. So here we have the memory laid out this way: 0 to F, or 10 to 1F, 2 to 2F, 3 to 3F. So the whole table represents the entire 128 bytes of memory. And in register banks, right, bank 0 is 0 to 7, and then their initial stack was A to F, or from 8 on, really it could go on forever. And globals, we're using 20 to 3F, right? These 32 bytes here. Now, one thing you might know with 8051 is there are these bit addressable bytes. So like the 20 to 2F, these bytes are also bit addressable. So you may want to use them in for cases where you need bit addressing and want to use bit instructions. Up to you. Anyway, then 30 to 3F, that's where we allocated some like save SP and other globals, right? And stack, it takes a 40 to 4H, 50 to 5H, 60 to 6H, and 70 to 7H for these 4 stacks. So then on power up, SP points at 7, PC is at 0, PSW is also 0. So that means it's selecting bank 0. Okay, and our globals are currently uninitialized and does a bootstrap jump. Now, so what does bootstrap have to do? First thing it has to do is to initialize these variables. So initial bitmap, right? So that would be all 0 because no thread is active. And it needs to create a thread for main, right? And so PC is now running bootstrap at step 1 here. So I'm writing bootstrap 1 to be the symbolic way to indicate the first step of bootstrap, okay? And PSW is still 0. After initializing, then what's next? Well, it creates the thread for main. So what can it do? Well, it could actually do a function call to create thread. We haven't written create thread yet, but assuming it does its job, then it's okay. Now, by calling create thread, it's still using this initial stack, but that's okay because we don't have any other thread. We don't have to worry about these registers to get trashed. Okay, so it's pushing the return address back to Bootstrap. So that would be return address at step 3 of Bootstrap by the time it returns. Now PC, because we're calling create thread create, so PC is pointing at thread create. Stack pointer has the return address, and then DPL/DPH has the address of main. Remember, we use, or SDCC uses DPL/DPH to pass the parameter, right? Or DPTR, because main itself is 2 bytes. It uses DPL/DPH. Okay. So then, inside the thread create, what does it have to do? Well, it needs to set up the context. So thread create is using this initial stack. But what do we have to do? Well, we need to put the initial values for ACC, B, DPL, DPH, and PSW on the stack. And then also, after these get restored, then what the stack has left is main's address. Then we can do a return to main. Even though you would think, I'm actually jumping to main, I'm not returning to main, but this is the mechanism, that trick I mentioned in the previous hour. That's how you can specify where you want to go to as a variable rather than as a hardwire address. If you really want to, you could hardwire main's address, but no, you don't have to. You just push main's address on this stack 0, not the initial hardware stack, the stack 0, because main is going to run as thread 0, right? You push main's address on here first, and you push the initial values you want to restore for ACC, B, DPL, DPH, and PSW, right? And then you call restore state, which will then pop the PSW back, DPH back, DPL back, B back, ACC back, and then does a return to main, and then it starts running main as thread 0. And that is the time when this hardware stack based at 8 is just discarded, okay? And so, when it's creating main, what it does is, it just pushes these, and then whatever stack on here doesn't really matter anymore. We already have DPL, DPH, and then it sets up the context, but then the stack itself is back to empty because by the time thread create finishes, it returns back to Bootstrap. So Bootstrap is back down to 7, okay? Because it returns from this, and then stack is empty. Stack was 9, now back to 7. and it's going to do set up the current thread ID. So how does it do that? Well, so the saved SP is 46 because by the time you restore, you want the SP to be 46 and then do the popping. Thread bitmap is initialized to 1 because at least now we have thread 0, which is, and then we do right alignment here. In Bootstrap, step number 3 is to set the current thread ID. That's easy. We just initialize current thread to 0. Not very hard. And then now the values have already been set up. So we do restore, and that's that macro. And what does that do? That pops off the content in reverse order, right? PSW gets 46, including the register bank selection. DPTR gets 45 to 44, B gets 43, ACC gets 42, and the address at, content at 42, right? And then 41 and 40 would have the address of main, right? 41 and 40 have address of main. So what do? You do a return. And then what return does? Pops off the return address, which is main, and jumps to main. That's how you bootstrap a thread. Okay? Everybody follows? Probably not, but stare at it a few times and you'll get it. It's really not that hard. Okay? So then the bootstrap basically calls thread create to set up the initial stack for main, and then does a restore state to that context, right? So saved SP already has the saved value, so then it copies that to SP. That's when the stack got moved from the initial hardware stack to thread 0 stack. Okay, then you can run. It restores PSW, which selects register bank 0, which is fine. The PTR, B, ACC all get the initial value. Stack 0 now has the return address of main. So when you return, it uses that stack, right? Thread 0 stack, and then returns to main. Now this stack is pointed at 3F, right? Because 41, 40 get popped, so it's pointing at one below. So now, what does that mean? This means even though main looks like a function written in C, and in fact it is, it doesn't have any return address. So if you finish main and it tries to return, it's going to be in trouble because there's not a valid address. Okay, so if you do it this version, it's really not meant for implicit return, right? Because we didn't push an address for main itself to return. We only return to main to start running main. But if you wanted support like POSIX threads, what do you have to do? Well, you would have to then have a way for main to return. What does it have to return to? Well, it returns to a thread exit, for example. All right? So that's an implicit call to thread exit. Otherwise, you have to explicitly call thread exit. Right? So now in main, this is what happens. So we just finished bootstrapping, which called create thread, and then create a context and restore state, then restore to thread 0, and main starts running. What does thread have to do? Main have to do? Well, main, you're supposed to write this, which is to create a thread for producer. Let's just start by creating one thread. Later, you can test 2 threads. It should work the same. And then call consumer to run the other thread. So now we're running stack 0 here. And now if it calls thread create, well, PC points to thread create. The return address would be the second step of main, right? So first step is create thread. So return, when it returns, it has to do the step 2, which is called consumer. So return address of main gets pushed on the stack, which is now 40 and 41. And then what does it have to do? Well, remember when you do create thread, you pass the function pointer to the function you want the thread to run, right? And what do you want to run? Because we want to run producer. That means the address for producer is passed as a parameter. And that is in DPL and DPH, right? And so thread create gets the DPL, DPH as the address that you want it to run, want a new thread to run. So what does thread create have to do? Well, similar to what we did before, you need to use a stack. Well, first it has to pick a thread ID that hasn't been allocated. So we would use that. I mean, that's based on bitmap, right? Before it was 0001, and next unused one would be thread 1's bit, right? So now it becomes 0011, and now so we know the ID would have to be 1, and so that means the stack is starting at 50, right? 50 hex up to 5 H. No, so 5F H. Or 5F hex. And what we do again is the bottom of the stack would be the address you want to return to. So by creating, you basically take the DP, LDPH, push them onto, well, you first have to save the stack, right? You actually have to, well, at least you know the location. So you put the content of producer's lower upper address bytes into location 50 and 51. And then the initial value, just like before, ACCB, DP, or DPH, onto the stack as well. Now PSW, on the other hand, is different. Why? Because remember, PSW includes the register select bits, right? Bits 3 and 4. And by restoring PSW, we also select which register bank it is. So bits 3 and 4, what are they? So lower bits are 0, 1, 2, 3. And then upper bits will be 4, 5, 6, 7, right? So now if it's binary encoding, 0 is 0, 0, 1 is 0, 1. So that means bit 3 should be set to 1, bit 4 should be set to 0, right? So in hex, if bit 3 is 1, that's 8 hex. And then bit upper address, upper byte, upper half byte is 0. So 0, 8 as a bit pattern selects register bank 1, right? And then the rest you don't have anything. So then, okay, so what we do then is to set up this context, and also because right now the top of stack is 56, save SP should be set to 56. Of course, no, this is just my illustration. Your implementation could be different. It might not be 56. So you shouldn't just hardwire the value 56 or 46 or anything on there. It should be whatever the stack is pointing at, and that's what you should be saving, right? Right? So it sets up the context. All that means is it initialize the value of the stack, but it hasn't changed its own stack yet. It still is running on the same stack as thread 0, okay? All we're doing is depositing some value into stack 1 so that it could be restored. Okay, so by the time thread create returns, well, what does it return? It returns the thread ID, which is 1 in the DPL. Then it comes back to main and then doing step 2, and it does a call consumer. It might as well do a jump to consumer, but okay, we do a call. And that actually means it does push the return address, but we never really use this address. Okay, but that's fine. And then the stack is now the 2 bytes of the return address back to step 3 of main, but we don't really use that. And then PC now pointing at consumer, and then consumer can start running. Okay, but that's still thread 0. Okay, so far we're only running thread 0. Thread 1 has been created, but we haven't run it. So now, while running consumer, what does it have to do? Well, it is running, and when it runs for, it can do polling this, polling that, and whether there's something to consume. If not, it does a yield. So what does yield do? Well, yield is a function call, right? And so by making a function call to yield, what does it do? It pushes the return address inside consumer on the stack at the time it calls yield. Remember? Right? And then thread yield, it takes control. Now the stack already has 4 bytes on there. The return address back to main and the return address back to consumer after the yield, right? And then so what does yield have to do? Well, yield has to save state. So what does saving state mean? Well, it has already consumer's address, so we don't have to push that, right? Unlike thread create because it wasn't running before, so we push the return address on there, which is the beginning of that function. But here, because it's a thread yield that calls it, the return address is already on there. That's fine. And then we just have to push ACC, push B, push DPL, push DPH, push PSW on there. And then that's how we save the state. Okay, that's all. Of course, we have to save the stack pointer as well. This time, stack pointer is no longer at 46. It's 48. Well, why? Because there's additional 2 bytes of the main address here, right? And in general, it can vary just because you may push more registers on there. Compiler may push a few other things, or what have you. So that's why you shouldn't hardwire these addresses. You should depend on the stack pointer, depending on whatever it needs to save, and then take a snapshot of the stack pointer, store it in this save stack pointer array, right? So right now it's 48, so we save 48, okay? Thread yield, that was first step, save state, and that was a macro, so no return. It just executes those instructions. Next, it has to pick a thread to run next. What does it have to do? Well, it's up to you. It's round robin, so you could do some bit shifting in the bitmap, and then go from there. Pick a thread to run, and so current thread was 0. Now if we pick thread 1 to run, then current thread gets changed from 0 to 1. And so, however you pick it, that's your policy, okay? And then once it picks a current thread, it could do restore state. Okay, restore state is another macro which does the reverse of save state. So what does it do? Pops off from the top of stack. Well, top of thread. It has to now. So we were running thread 0, but after setting this to thread 1. As soon as you start doing restore state and switch the stack pointer based on the current thread, right? That's what the restore state has to do, right? So restore state as a macro says, oh, my current thread is now thread 1. Thread 1 has a saved stack pointer of 56. So it goes to 56, and that's your top of stack. As soon as stack pointer changes, you switch the thread, right? You completely switch the thread. But then it's still part of restoring that state. So pops a PSW. Now PSW contains a register bank number. So it also, as a side effect, restores your register bank. So now bank 0 is no longer active. But as soon as you pop PSW from stack, then bank 1 becomes a new register bank, and DPH, DPL, BA, and then now these are all done. Finally, it does a return, and so it returns producer. Okay, so that's how producer starts running. So on finishing thread yield, so that's so it sets SP to the stack once a stack pointer restores, which selects bank 1, DPTR, ACC all gets restored. Stack 1 has a address of producer. There's a return to producer, right? And then, and then again, of course, producer should not return because we haven't done the thread exit yet, at least not in this implementation. If you do, then it returns to some unknown place, stack underflows. Okay, so this is a summary of cooperative threads. Thread yield saves the state of current thread, selects the next thread, restores the context of the newly selected thread. And the context includes return address plus all this saved values of these registers that are on 0 to 7, and R0 to R7 are saved in the register bank. Okay, so now this version, remember we are not implementing thread exit yet, because exit is more than just recycling the thread. If you want to be compliant, there's the join or detach. You probably remember from previous weeks. And so we're doing just the simplest version. The others, I think, are a lot easier, right? So open issue really has to do with the scheduling policy. Right now, we do the simplest one, and then preemption will be done after you get the cooperative version working, because after you fully understand this, preemptive is actually not as hard. It's just tricky because of race condition, and that's where you need to do additional things to make sure things happen atomically. Later we'll revisit the issue of join and detach in conjunction with the thread exit. So I'm gonna do a quick demo to show you that this actually works. And I have my source code here. I do make clean, okay, and make. So this works, and even though you have warning, that's actually not a problem. These warnings because we do inline assembly and the compiler doesn't understand or doesn't see what we do with the inline assembly, so it's giving us some warning. So that's okay, and especially like this FP is unused. Why is it unused? Because as soon as we get the parameter passed, we do it all in assembly, right? Parameter is passed in DPTR, or actually function pointer DPTR, so 2 bytes. But in our code, because it's all written in assembly, it doesn't see it used, so it thinks, oh, you haven't really used this argument FP. Well, we do. We know what we're doing, so don't worry about this, okay? So this compiles, and do you want to see the source code? No, I'm not going to show it to you. You get to have some fun, because I had fun writing this, so I shouldn't deprive you of the fun. Okay, so load, test co-op. Okay, that was just freshly compiled, right? And let's reset it. Assemble, right? And then, so run. And then here's what you should look at. Yeah, so it's outputting to UART. Yeah, so it is producing and consuming, outputting to UART. And how do we know? So let's take a look at the stack. Okay, so now there's stack here. 40 is for thread 0, 50 is for thread 1. So it is actually, I mean, a little fast, right? And I have a few global variables, and in fact, I can even read binary or read hex. This is thread 0, thread 1. It's bouncing between thread 0 and thread 1. So, yeah. And then if you look at PC, it's actually doing switching between 2 threads. Okay, so then, and there's one bank here, another bank here, right? So let's pause and then maybe reset it. Do a little bit slow motion. This is too fast. Right? 2, 1. Assemble, and then let's do step. Is there a step? Yeah, here it is. So it is the jump, right? L jump to 62. And how do you know what 62 is? Well, remember, you can always go back and reference your there's a so you have all these things. The map, okay, map. Okay, so there's can we find 62? Yes, bootstrap. Yes. Okay, so that means it is doing bootstrap. Okay, that's L jump to 62, and then we do a step. So 62 is bootstrap, and then it's stepping, and then move dptr. Oh, remember this one? So move 04ch to dptr. What is that? You could probably guess what it is. When you do something to dptr, you're probably passing a parameter, right? What are you passing? Well, okay, 0, what is it? 4c. Not surprisingly, main. We are creating the initial thread for main. Okay, so, and then where does it jump to? Thread create, right? That's at address 8a. So if we step a few times, so calls address, not surprisingly, 8a. It's calling thread create right there. Okay, stepping, and then it's doing its thing. Okay, so it's really doing its job, and then so it's certainly doable and not very hard if you follow the directions I give step by step. Make sure you understand completely. You can't skip anything. You can't skip it, not even a bit. You have to understand 100% for this to work. But in general, that's what system software is all about. You gotta have complete understanding, okay? No skipping details, right? So, but after you've done, get this working, I think you'll have much better idea, much better feel for what system software is about. And then, you really gotta get the cooperative threads all working before you move on to the preemptive one. Okay, so look for like 2 Google Docs this week. One is a review of all the concepts you need, and then the other is really a guide for the checkpoint for doing the cooperative threads. Okay, see you Wednesday.